Welcome to this course on linear algebra for AI and ML, and we will start with the first lecture. And today we will get introduced to the concept of vectors. So vectors are something that are really very important for us, and especially it has a lot of applications in artificial intelligence and machine learning. So we'll start by defining a vector. So a vector is ordered finite set of numbers. So a vector is an ordered finite set of numbers. Finite list of numbers. In general, this finite list need not be of numbers, but it can be of objects. But as far as our course is concerned, we will only think of finite list of numbers. In general, this list may also not be finite. So finite is a keyword. This list may not be finite, but as far as our course is concerned, we will always consider a finite list of numbers. So typically these vectors are represented as column vectors. So typical convention for us will be column vectors. So for example, you can write down the vector 0, -1, 3, 2. This can be one vector. There can be another vector which consists of -1.3 and +1.3. There can be another vector which contains 1, 0, 1, 0, 1, 0. So these are the examples of vectors. So these are the type of vectors that we will really look at in this particular course. Because the list is finite, we can count how many number of theirs are there in a vector, and typically a vector of length n is called as an n vector. So a vector of length n will be called as an n vector. So n vector implies that there are n elements or n entries. So each of these numbers that I have written in the list, they are called as entries or elements. Entries, elements, coefficients. So these are different names. These are different names for these entries. So this is what we have, n vectors. And more mathematically, so I will denote these vectors notation. I will denote these vectors by these letters A, B, C, X, Y, Z. By small case letters, I will generally write down the vectors A, B, C, and A1 will represent first entry of vector A. Okay, but there is an ambiguity of notation in this particular case. What is ambiguity? Ambiguity is that suppose I consider A1, A2, A3 to be vectors, then how do I represent the first entry of A1? So suppose A1 sub j will represent jth entry of A1. So when I write down this A1, so if this the first entry of A1, in this particular case A1 is the number. A1 is the number. But when I write down vectors A1, A2, A3, then A1 actually is a vector, and I am looking at the jth entry of A1, I will denote it by A1 sub j. So this is the notation which is slightly confusing, but over the time you will understand what I am really meaning when I write down these things. Okay, so the first thing that we will like to talk about is equality of vectors. So let A and B be two vectors. Let A and B be two vectors. You call A is equal to B, A is equal to B. This is true if and only if. So these double arrows mean if and only if AI is equal to BI for every I. So what is the first condition for two vectors to be equal? they should be of same length. So A and B, they are both n vectors. Okay, n vectors, same length. If the vectors are not of same length, then you cannot compare the two vectors like the way we are defining it right now. And if they are n vectors of same length, then you call them equal. A is equal to B. If AI is equal to BI for every I belonging to this set 1, 2, 3 up to n. So these are all notations that you have to remember. So this notation is if and only if. So this is same as defining. This is for every. This is for every. Okay, so for every I. And this small epsilon that I have written, that really means it belongs to this particular set. So that's the notation that we are saying, and we say that the vectors are equal if AI is equal to BI for every vector. One more important notation that I will use instead of representing n vectors, I will say A, B belong to a set R power n. So where this R is actually the set of real numbers. Okay, set of real numbers. I'll come little later, and sometimes I'll call field of real numbers. So we'll see what it really means, but not immediately. So this is field of real numbers. And when I am having R to the power n, then this R is really telling me entries are coming from n. Entries are coming from R. And this n which I have written on top, it is telling me the length of the vector. So you can see the importance of this particular notation R to the power n. You can change this R to the power n to F to the power n. And what would this F to the power n would really mean? So in order to make it more general, I will just say F to the power n. And what would this F to the power n means? F, entries are coming from F, and M is telling you the length. So if you understand this notation, then this notation is one of the most important notations in mathematics, R to the power n. And once you understand this notation, I will always write down vectors A and B not as n vectors or n length vectors. I will prefer to write them AB belonging to R to the power n. And when I say R to the power n, I mean that it's an n length vector with entries coming from the set of real numbers. The set of real numbers is very important for us, and almost all the examples that we will consider in this particular course, the vectors will have real entries. So the vectors will always be R to the power n vectors. There is one more thing, that you can block vectors. So that block vectors is basically, suppose A is a vector, you can construct this vector by 3 different blocks of vectors A1, A2, A3, and I will say A1 belongs to Rn1, A2 belongs to Rn2, and A3 belongs to Rn3. Then this vector actually belongs to Rn1 plus N2 plus N3. So this vector will have N1 plus N2 plus N3 length, and in particular, now you can see in particular, if A belongs to Rn, then all AIs are in R1 or nothing but they are real numbers for I is equal to 1, 2 up to n. So every vector in Rn also can be thought of as a block vector, each block of length 1. That is something that is very interesting, but you can just note it down. So this is what we really mean by block vectors. So these block vectors will be really very important, because little later we will be doing some block operations on the vectors. Okay, so this is something that is important. And one more thing that I would like to draw your attention to is indexing. So when we do indexing, we will always say that vector x. So suppose I consider a vector x, then this vector x is x1 up to xn. This vector belongs to Rn, it's an n vector. Then I will always say that the list, I will say the first entry is indexed with 1, second entry is indexed with 2, so on and so forth. The last entry is indexed with n. There are certain programming languages like C where the indexing starts with 0, so the first entry will be 0th entry, second entry will be the first entry. The index will be 0, 1, 2 up to n minus 1. But as far as linear algebra theory course is concerned, we will always consider the indexing starts with 1. When you start doing programming, you will have to make the adjustment based on which programming language you use, how the indexing works. Okay, so with this introduction, let us see some examples of vectors. Okay, one of the most important vector is zero vector. Okay, so this vector plays a very crucial role. And what is that zero vector? I will denote it by 0. So now you realize that this 0, when I write down, this 0 equal to 0 up to 0 belonging to Rn. So it is basically a list of n zeros. But you have to understand the difference. The zeros that I am writing here are real numbers. These zeros are actually the real numbers, while this 0 that I write down here is actually a vector. It's a zero vector. It's a list of n zeros, and this guy, this 0 that I have written on the left hand side, this particular 0, this 0 belongs to Rn. So this is a vector Rn. Okay, it's a vector 0. So though I write the same notation for both these vectors and numbers, this 0 on the left hand side, the highlighted by red, is actually a vector. So that's a zero vector. It's a very important thing. The similar way I can define another very interesting vector, that is ones vector. Okay, so this ones vector is really very important, and from the names you can guess it. All entries are 1. All entries are 1. Okay, so this is ones vector, and I will try to remember it throughout the course to write down this ones vector as 1n. So this 1n belongs to Rn. Okay, so all the entries are 1, so I will try to write down the real entries as this one and the vector as this 1n. Okay, so this is 1n. All the entries are 1. This is another example. The next example is unit vectors. So these unit vectors are really very important, and they play a very important role in linear algebra. So I will denote them as E1. So E1 is 1, 0, 0, 0. So I have first entry as 1 and all other entries are 0. That's my first unit vector. Similarly, E2 is second entry is 1, all other entries are 0. That's my second unit vector, and so on and so forth. I will have EI, where only the ith entry is 1 and all other entries are 0. And finally En, which is En, all the entries are 0 except the last entry. So these are the unit vectors. These unit vectors are really very important, and little bit of notation if you really want to understand. EJI. So I am looking at the jth unit vector and I am saying what is the ith entry of the jth unit vector. So this will be equal to 0 if I is not equal to j. I is not equal to j, and it is equal to 1 if I is equal to j. Correct? So the entry is 1 if I is equal to j. E2, 2. The second entry of E2 is 1, all other entries are 0, for example. So you can check this is the unit vector. These unit vectors are really very important, and these special vectors will really play crucial role. Okay, so these are the special vectors. The first special vector is 0 vector that we looked at. The second special vector is ones vector that we looked at, and the third is unit vectors. Okay, so now let's see why these vectors are really very important and where do these vectors really come into the picture. Okay, so some examples of vectors in AI and ML. Okay, so some examples of vectors. Okay, so the first example is color. So what is color to do with it? So I will have a vector of length 3. So I'll be considering a 3 vector. Okay, so I'll consider a 3 vector. So the 3 vector will have 3 entries, 1, 2 and 3. I'll write them here. And those 3 entries will correspond to the intensities of the basic colors red, green and blue. Red, green and blue. So suppose if I write down the vector 1, 0, 0, then the color that I am talking of is basically red. If I am talking of 0, 0, 1, then the vector that I am talking of, then that's blue, right? And if I have some alpha, beta, gamma, then I have a red color with intensity alpha, green color with intensity beta and blue color with intensity gamma, and when I mix these three together I get certain color. Okay, so for example, if you have all of them to be equal to half, or for example if you take 1, 1, 0, that is you mix red and green, so the color that you will get is yellow. So that's the color that you get, yellow color, if you mix red and green, and so on and so forth. So this is one example where colors come into the picture. So in order to generate all possible colors, I think the entries that you will have to take for alpha, beta, gamma in general will be the intensities between 0 to 1, and then you can generate all possible range of colors that you want to generate with the basic colors RGB, red, green and blue. Okay, so this is one example where vectors might come into the picture. Another is certain values across population. Okay, another is certain values across a population. So for example, the population is of size n. Population is of size n. Then you will get an n vector. And what will this n vector have? The n vector will have the entry, ith entry, as the value recorded for the ith person in the population. So for example, an n vector can be a vector of all the heights of the people in the population. So it can be h1, h2 up to hn. This is in Rn, where hi represents height of ith person, height of ith person in the population. So this is another example where vector comes in handy. This is really very straightforward example, but this is very important in one of the applications of AI/ML, regression. So this thing you will always come, this will always be the example that you will see. That's how the data is represented in a regression setup. So that is something that is very important. So that's why I mentioned this example here. The first example that I mentioned, you will see that in imaging. Okay, so the first example of the vector color you will see in imaging. Okay, so that's why that example was important. Another example that you can see is that of time series. So a time series can be represented as a vector. So suppose you like observing the stock market and the price of stock with respect to time. So you are monitoring the price of stock every minute in a day. Okay, so suppose for example you observe the stock price in first 1 hour. So you will have 60 values and you will have a time series of these values, right? So this time series that you have, for example, these are the values that you will have, that you would have observed, right? These are the values that you would have observed. So these values, so these 60 values, for example, you will put in the vector. So P1, P2 up to P60. Okay, so I will write n in general. So these are the values at n time instance. So this is 1, 2, 3. So this is the time axis. So this is the time axis in the time series. And these are the price values, right? Price of one particular stock. So you can collect those values together in a list and write it down in the list. So Pi, ith time instant value, right? So that's the interpretation. So that's how you can look at the vectors. So in a time series, these vectors comes. Time series analysis is a very important analysis, and there you can use this vector representation. Another place where you can have this is imaging. Okay, so the first example and this example you have to consider together, but for some reason we are considering them separately. Little later in this course, when I introduce the concept of tensors, I will consider these two things together, the example 1 and example 4 that I have mentioned. So in images, what really happens is you have an image, and this image, so I will consider a gray scale image or black and white image. And what happens is I have divided this whole image into the pixels, and at each pixel, so basically this is a very primitive 4x4 block, and I divide it into 4x4 16 pixels, and I read the value, the grayscale value which is present in this pixel, and that's how I actually read an image in a computer. So basically for me the image is nothing but the values that I have in these 16 places, right? So that's nothing but collection of 16 values. So that collection of 16 values I can actually represent using a vector. So suppose there are m divisions on x-axis and n divisions on y-axis. So there are mn number of pixels that I am really looking at. Then the values I'll store. So I will generally take the first column, then put the second column of pixel values below the first column. So I'll have n values here for the first, followed by another n values. So these are the blocks of vectors I am putting one below the other, and this vector belongs to Rmn. Okay, so this vector for me basically is the image, right? So this is something that is really very important. So in order that you understand what I have done, I will highlight this first as green, I put this as green, then the second column is red, then I follow this second column here, and so on and so forth. So that's what I have done. I have done the block vectors. Okay, so this is the first column followed by the second column, and this is nothing but my image. Okay, so this vector x is basically nothing but the image for me. So that is something that is important. Another example of vectors that you will encounter is in natural language processing, and the vector that I will consider is of word counts. Okay, so this vector of word counts is something really very important. And suppose I have a dictionary D is the dictionary, and that dictionary D has n words. So this dictionary D has n words. Okay, so this dictionary D has n words, and I am looking at a document. Okay, I am looking at a document. So document has certain text written in it, and then what I am going to do from that document is I will write down all the words in the dictionary D1, D2 up to Dn, and I will count how many number of times this word D1 in the dictionary comes into the document. So suppose 0, 2, 1, something, 0. So this is a vector in Rn. This is a special vector in Rn. So this vector will always have non-negative entries. Okay, so in the imaging example, the vectors will always have intensity values. So the intensity values will always be between 0 and 1. So the vector entries will always lie between 0 and 1. So like that, this vector will always have entries which are non-negative. They can be 0 or positive entries depending on how many number of times the word D1 appears in the document. Okay, so this vector generally is sparse also. Okay, so we will come to that. So this vector generally is sparse also, because you do not expect that all the words in the dictionary are present in the document. So there will be many 0 entries in this particular vector. But this type of vector, the vector of word counts, is really very important, and this vector really plays a very crucial role in the natural language processing applications. Okay, so these are certain examples of the vectors. So now what we will do is we will move on to the second important concept relating vectors, that is operations of vectors. Okay, so what we are really going to do is, now after understanding what is a vector, notations, special vectors and some examples of vectors, we want to understand important operations of vectors. The two important operations that we want to look really is vector addition, and second is a scalar multiplication. So these are the two important operations that we want to focus on. So the first operation is addition. So let x and y be two vectors in Rn. Then what do I mean by addition of two vectors, x plus y? So x plus y, so suppose x1 up to xn is the first vector and y1 up to yn is the second vector. Then the addition is x1 plus y1, so on and so forth, up to xn plus yn. That's the addition of these two vectors, x1 and x and y. So this is addition. Similarly, I can define subtraction of two vectors. So x minus y is x1 up to xn minus y1 up to yn, and it is trivial to define x1 minus y1, xn minus yn. This is subtraction. Okay, basically I will not distinguish between these operations, addition and subtraction, for a reason that when I introduce scalar multiplication, we can see that subtraction is nothing but addition only with a certain scalar multiplication applied to y. So that's why I don't regard subtraction as a different operation. This is what we have. And certain quick observations about this are the follows. Okay. So these I will list as properties of vector addition. So what is the first property? So I will consider x, y, I'll consider x, y and z to be three vectors in Rn. So they are all same length vectors. So as you have observed, by definition, I am saying that when I want to add two vectors, the vectors should be of same length. Okay, if the vectors are of not same length, then I cannot add the vectors by definition. So if I have three vectors x, y and z, then the first property is commutative. What does that mean? That means that x plus y is same as y plus x. I add x plus y, that addition is same as y plus x. Associative. Okay, so associativity is another property of this operation, which means that x plus y plus z is same as x plus y plus z. Okay, so the order in which I add, in case of there are several things that I want to add, that order really is not important. I can add in any order whatsoever I like. The final outcome will be the same. The bracketing is not important. Okay, so what I really have here is that I will write this as x plus y plus z. Okay, that is something that is really very important. The third thing is 0 in Rn. Okay, for this 0 in Rn, the 0 vector in Rn, what we have, x plus 0, because of commutativity, it is same as 0 plus x, and this is same as x. Okay, so 0 is a very special, very interesting vector, 0 vector. You add 0 vector to any vector x, you still get the same vector x. Okay, so this 0 is called as additive identity. Okay, this is called as additive identity. And the fourth property is a very simple property based on the third property, is that for every x in Rn, x minus x is 0. So I subtract the same vector from itself, I get a 0. Okay, so this minus x is actually called as additive inverse. Why is it called additive inverse? Because I do x minus x and I get 0 vector, which is nothing but identity. So this minus x is basically an additive inverse. So these are very important 4 properties of this particular operation of vector addition. I will recall these properties at the end of this lecture to define a very important object in mathematics, which is called as vector space. That vector space is actually the building block in linear algebra. So we'll define it at the end of the class today, but for that I need these 4 properties. Okay, so let's remember these 4 properties of this operation vector addition. Okay, so now once you have this vector addition, what is the standard, like I will not so the geometrical interpretation, right? So for example, if you have 2 vectors in R2, so suppose this is one vector and this is another vector in R2, so because I can put an arrow, so suppose this vector is x and this vector is y, then what is the meaning of vector addition x plus y? The meaning of vector addition x plus y is using parallelogram law that we all studied in our school days. I will complete the parallelogram. So after completing the parallelogram, what do I get? I get this particular vector. So this vector is x plus y. That's the vector that I get here, right? So that's the vector x plus y that I get here, the vector x plus y. This is the addition, it's the diagonal of this parallelogram. Okay, so this is the parallelogram vector addition, parallelogram law of vector addition, right? So this is what I get. So this is what I get for my vector addition. The interesting thing is that what does this vector addition really mean with respect to the examples that I have considered, and at the same time let's try to look at this. Okay, so let's try to understand what those examples were and how we can. So the first example that you can consider is word counts example, the last example that we had. So D was the dictionary and N is the number of words in the dictionary, right? Number of words in the dictionary, correct? And suppose I consider 2 documents, document 1 and document 2. Then document 1 is basically a vector x and document 2 is basically the vector y. Then the addition x plus y really means that how many number of times a particular word appears in both the documents, right? That's the meaning of the vector addition x plus y. And similarly x minus y will tell you how many times a word in document 1 appeared more than document 2, the same word, right? So that is something that is really very important. And the negative values in x minus y will tell that the word appeared only in document 2 and not in document 1. So that is something that is really very important. So that is the meaning, that is the interpretation of these 2 operations, vector addition and vector subtraction, x plus y and x minus y in this particular thing. The other interesting example of vector addition we can consider is that audio addition. Okay, so what is this audio addition? So let A and B be audio signals. Okay, so they are audio signals, or you can consider them as time series of the same length, audio signals of length n. Okay. So for example 1 minute, and what have I done? So they are 1 minute, one minute length audio signal. So what do I mean by 1 minute? So suppose I record the audio signal at every second. That's a very bad audio signal, but let's suppose that I record it every second. Then A will have 60 entries and B will have 60 entries. And what is A and B? A and B are 2 audio signals. So A, for example, is the signal which is somebody is singing. So for example, you are singing, and B is the signal where somebody is playing tabla, but they are recorded separately, and then I add them together, then I get A plus B, then A plus B signal, if you play the audio signal, then it will have you singing as well as somebody playing tabla together. So this is the technique generally nowadays people use, sound engineers use. So they do something more sophisticated than just A plus B. So that sophistication will come when we introduce something which is called as scalar multiplication. But for the time being, this is what you can do. So nowadays you see the online concerts happening, right, in Facebook and all that stuff. So what generally you will do is that somebody will record music, so somebody will be singing, for the same time instant somebody will play tabla in their home, then these two signals will be added together and then you get music concert. Okay, so that is something that is really very interesting. So this audio signal addition is something that is really very important. The third is a time series example. So time series addition. So what is this time series addition? So this time series addition is something very, very useful. So suppose there are in our stock market example, you are monitoring stock of a company red and stock of company green. So when you add these two signals together, so this is X and this is Y, and when you add these two time series together, that's the price of both the stocks together. So when you want to build a portfolio of stocks, this type of addition and subtraction really becomes important. Again, if you want to give an advice of how to invest, then only addition is not important. The scalar multiplication will also come into the picture. That sophistication will add through scalar multiplication. But that's meaning. X minus Y similarly will tell you difference between the stock values at those particular time instances in this particular time series. Okay? So that is something that is very important. So that's the first operation that we really look at. The second operation that we want to look at is scalar vector multiplication. Okay, scalar vector multiplication. Scalar vector multiplication. And what is the scalar vector multiplication? I'll consider a scalar alpha in real numbers, a vector x in Rn. Then what do I mean by alpha dot x, which is same as alpha x, which is nothing but alpha times x1 up to xn, which is nothing but alpha x1, so on so forth up to alpha xn. So I multiply this alpha scalar to each entry in the vector. That's what I do, right? So this is straightforward application. So what are the properties of this scalar multiplication? Like the properties that we had for addition, there are several properties that you can look at. So if I look at two scalars alpha and beta and multiply them, so I get this for alpha and beta belonging to R and x belonging to Rn. So this is what happens to the scalar multiplication. The second property is alpha beta into x is same as alpha into beta x. Okay, so this is again true for alpha beta. The third property is alpha into x plus y is alpha x plus alpha y. Correct? So I can have this particular property that I add vectors first and do scalar multiplication. That's same as this particular thing. So this is something that is really very important. So these properties, and the fourth property is for scalar 0, and a vector in Rn. This is something very interesting that you should understand. 0x is equal to 0. But when I write this equation down, 0x is equal to 0, you have to understand that this 0 is a scalar, but this 0 is a vector 0. So this is the 0 vector in Rn. So this 0x is equal to 0 equation, when you see, Generally nobody will distinguish between which 0 is which 0, but you have to understand which 0 is which 0. The one on the left is actually the scalar 0 and the one on the right is actually the vector 0. So that is something that is really very important. So what is the interpretation of this scalar multiplication? So you go back to audio signal case. So you go back to the audio signal case, and in this particular audio signal case, what is really happening? If you have the audio signal X belonging to Rn, that's the audio signal that you have, and you have some alpha greater than 0, then when you have alpha times X, that is same as saying you are increasing the volume. The signal is same, but you are increasing or decreasing the volume based on what is alpha. So suppose alpha is equal to half, then you are decreasing the volume. If you increase alpha to be equal to 2, then you are increasing the volume. Okay, so geometrically what is really happening? Geometrically, if you have the vector x, if this is the vector x and your alpha is equal to half, then you are not changing the direction of the x vector, but what you are doing is you are just rescaling it. So x is equal to alpha is equal to half will result in this particular vector, while if you have alpha is equal to 2, then you will get this particular vector. Okay, so maybe I should use a different color. So alpha is equal to half is this, and when you use alpha is equal to 2, then alpha x is this particular vector represented by b. So if you have alpha is equal to minus 1, if you have alpha is equal to minus 1, then you will get this particular vector. Okay, so technically when you have alpha less than 0, if you think vectors as vectors in physics, then you change the direction. If alpha is greater than 0, you still are in the same direction, you are just doing the scaling. Okay, so as linear algebra interpretation of things grow on you, vector space interpretations grow on you, you will not even make distinction between alpha is equal to plus 1, alpha is equal to minus. Okay, we will say that you stay on that subspace. So we will get into that little later, but for the time being, this is what really alpha does. Okay, so this is the geometric interpretation, and for this audio signal, so this is basically quieter audio. Okay, same audio, you are little bit quietening it, and alpha greater than 0, you are making it loud, you are increasing the volume, so to speak. That's what really happens. So we have looked at two important operations. The two operations on vectors being vector addition and scalar multiplication. And once you have these two operations together, I would like to combine these two operations into something which is called as linear combination. Okay, so what I really would like to look at is linear combination. Okay, so what is linear combination? Linear combination is you take let x1, x2 up to xn be vectors in Rn, and let alpha 1, alpha 2 up to alpha n be scalars in R. Okay, so I take n scalars and I take n vectors and I form a new vector y, which is alpha 1 x1 plus alpha 2 x2 plus alpha n xn. So that's my linear combination of these vectors x1, x2, xn. So this I can write down in short summation sign alpha xi, I going from 1 to n, is obviously a vector in Rn. So y is a vector in Rn, and we call y to be a linear combination of these vectors x1, x2 up to xn. So this is an operation. So this operation is this linear combination is obtained by looking at two operations. What are the two operations? So these additions are actually vector additions, right? So these additions are vector additions, and this operation alpha 1 x1, alpha 2 x2, these operations basically are scalar multiplications. Okay, so if you understand what is really happening, then immediately what you can see is what is happening in your audio signal example. What is happening there? So you have different audio signals x1, x2 up to xn. So these audio signals, so suppose x1 is a signal where somebody is singing, x2 is a signal where somebody is playing guitar, x3 is a signal where somebody is playing drums, and so on and so forth. So different instruments are being played in different places in different audio signals. One audio signal is actually the song that you are singing, and then you multiply them with vectors alpha 1 x1, alpha 2 x2, alpha 3 x3, alpha n xn. So those alphas are basically determining the intensity. The alphas are determining intensity. So suppose x1 is the song that I am singing little lower voice, then alpha 1 can enhance. Alpha 2 is like tabla volume, so table wala bahut जोर से बजा रहा है tabla, then you can reduce the tabla by taking alpha between 0 to 1 and so on and so forth, and then you can add all these things together, and what you get is actually the audio signal which we hear eventually as a music concert, for example. So the audio engineers, the sound engineers are actually in real time determining what is this alpha 1, alpha 2, alpha n. Many times you listen to the concerts, they say thoda ye badhao, thoda ye kam karo. So basically they are adjusting those alphas, and by adjusting those alphas they are combining these different audio signals alpha 1, x1, x2 up to xn with different intensities alpha 1, alpha 2 up to alpha n, and that linear combination alpha 1 x1 plus alpha 2 x2 plus alpha n xn actually is the audio signal, the final audio signal that you listen to in the music concert. So that's the real importance of audio signals. That's how you can understand what is happening in the linear combination. Okay. Another interesting thing that you can think of is linear combination of unit vectors. So unit vectors is something that we had looked at earlier. So what do we mean by linear combination of unit vectors? That's something that's really important. So E1, E2 up to En are the unit vectors in Rn. So for example, now you would have realized that in Rn there can only be n unit vectors. In R5 there will be only 5 unit vectors, and so on and so forth, right? So you have those unit vectors E1, E2 up to En, and for any vector x, which I will represent as x1 up to xn in Rn, you can see this x is basically x1 E1 plus x2 E2 plus xn En. So very interesting thing to observe here is that every vector x in Rn is a linear combination. And this linear combination, I will just use the word unique, though I will not tell the meaning of this word right away, is a linear combination. In fact, I will say it's the unique linear combination of unit vectors. What I want you to think about is this word unique. Okay, I want you to think about this word unique. This word unique I will relate little later when we talk of important concepts of vectors like linear independence, linear dependence, basis. But right now I don't want to worry you too much about it. But you can think of this word unique and try to understand what it really means. Okay, so this is something that is really very useful. This is something that is really very important. Another special linear combination that we really want to, special linear combinations. Okay, so another special linear combination that we really want to look at is you have n vectors x1, x2 up to xn. So you have these m vectors in Rn. So you have these m vectors in Rn, and you take alpha 1 equal to alpha 2 equal to alpha m, which is equal to 1. Okay. Then what is this linear combination Y? which is nothing but alpha I xi, going from 1 to m. This is nothing but x1 plus x2 plus xm. So addition of vectors basically is a special linear combination. Okay, addition of vectors is a special linear combination where scalars are equal to 1. This is something interesting. Okay, so in the same example, so suppose I have x1, x2 up to xm belonging to Rn, and if I take alpha 1 equal to alpha 2 equal to alpha m is equal to 1 by m. Suppose this is what I take, all the alpha I is equal to 1 by m. Then what is this y, which is nothing but alpha I xi, I going from 1 to m. This is nothing but x1 plus x2 plus xm divided by m. So I am actually taking average of vectors. Okay, so this averaging of vectors is again a linear combination. So I will define average of entries in a vector little later. That's a different thing. This is what I am defining as average of vectors itself. So this is called as averaging. So averaging is a linear combination, adding is a linear combination. So one of the interesting linear combinations that I look at is basically when I look at x1 and x2 to be only two vectors in Rn. Okay, in particular I take them to be equal in R2, and I look at this alpha into x1 plus 1 minus alpha into x2. Okay, so this is the linear combination that I look at. So this linear combination, what does it really mean? This linear combination is addition of these two vectors alpha x1 and 1 minus alpha x2. But if I vary alpha over all possible real values, so this alpha is allowed to take any real value, and then I look at the locus of this y as alpha. Okay, then this is nothing but the line passing through the points x1 and x2 geometrically, and this particular linear combination is called as affine linear combination. Affine linear combination. And in particular, if I choose in this particular linear combination alpha x1 plus 1 minus alpha x2, where alpha belongs to 0, 1, and then for any alpha in 0, 1 I find out what is alpha, I get line segment joining these two vectors x1 and x2, right? So pictorially what is happening, I have this point here, so this is my vector x1 and my vector point x2 is here, and if I look at the affine linear combination, then I get the entire line, and if I just restrict myself between 0 and 1, I will only look at this particular part, which is the line segment. Okay, so that's basically the interpretation that I am really looking at when I say I am looking at this alpha 1, alpha 2. Okay, so that's what I will get. So this is the line and this is the line segment, and this particular thing is called as convex combination. Convex combination of these two vectors. Okay, so this is what we have done so far. So we defined what is known as vectors. We saw some special vectors, examples of vectors. We defined two operations on vectors, vector addition and vector scalar multiplication, right? So I will just write it down as scalar multiplication. So these are the two operations that we studied. Okay, and then combining these two operations, we realized what is linear combination of vectors, right? We understood what is linear combination of vectors. Each of these concepts were accompanied with some special examples, some special scalar multiplications, their interpretations in the examples that we had seen earlier. and linear combination, geometrically what it means, with the special example of audio signal, what it really means physically. That's why we understood. And we have listed the properties, of these two operations, right? So that's what we have done. So the listed properties of these two operations is where we'll start our next lecture. Thank you very much.